So the timer says started. Good morning all together. Unfortunately, all the nice heads are gone except my personal one. Either through nicely asking me early enough, showing up first, or bribing like the Italian mafia is doing that. So I usually like to get a glimpse of my audience. Who has actually watched my CPPCon talk of last year? Okay, unfortunately, you will not see that much new stuff, but a little bit. Okay, all the others, welcome to Safe and Sane C++ class types. Who is not programming in C++? Okay. Then I hope Anders gets some new ideas for quizzes. Maybe not. So Patricia asked a question about what are the common bugs that people write in C++. And there was kind of a very similar distribution. The same question was asked for C, like use after free deletes, meaning using a dangling referencer pointer, memory leaks, double free deletes, null pointer dereference. And then I and some others said, well, we don't get these bugs. Not anymore. Because from C++ 11 on, we have the mechanics to actually treat most of them well. So my students don't use plain pointers. And it's doable quite easily once you know how. And that's one of the things I like to teach you. So when I looked at that, I said, okay, memory leaks, there's no reason to have a memory leak in C++ anymore. Double free delete, there's no reason to have a double free delete in C++ anymore. Null pointers, well, this requires a little bit of discipline, but very often, where in the past pointers were passed around, you no longer need to pass around pointers. Just pass values. If you really care, maybe reference, but even values can get you better code than just passing a const reference. And in modern C++, user-level code, there are no plain pointers, full stop, and no C-style arrays. You might still need to employ these mechanics, but then only tightly encapsulated, like if you're doing classes that are similar to what the standard library provides, for example. Then you might need to use pointers to manage stuff, but that's not something you would expose to the users, except under the disguise of an iterator. Everybody doing that? Who's not doing it yet? So you have something to change for tomorrow. Now, when preparing these talks, I thought about, okay, quite recently, or maybe 2 years ago, I started to care about, okay, safety critical systems, like self-driving cars, like elevators, which we all experience this week. And also, I've seen regulation code and even heard stories on, or even reviewed safety critical code, which I cannot tell you which one. If you see what the code quality is, it's sometimes disturbing. And yesterday, Anastasia told us, well, embedded programmers, almost 90% never heard of unit tests or write them. That's criminal negligence. So you just should no longer write code like we did 50 years ago. And maybe even 50 years ago, it was higher quality than 20 years ago. We know how to do it better. So there's one thing is about, okay, is it safe? Doesn't it do harm? But there's also the dimension of sane. And many older safety critical coding guidelines pretend to be safe, but more on the ill-advised side. For example, I can say that now because I'm working on the new version, MISRA C++ 2008. Anybody had a look at that? A few, okay. So that's a programming guideline, pretending to be a programming guideline for C++ users, written or published in 2008. It was written by Ada programmers for bad C programmers who pretended to program in C++. And a lot of things that were in the language in 2000, since 1998 or even earlier, have not been considered well enough for modern use. So we hope that the next release of the MISRA C++ guidelines will have a much more modern feel to that, addressing C++ 17, 11, and 14. There's still some stuff where you require high discipline, like, okay, I'm wearing a hard hat so nothing bad happens, and I pay attention to what's going on. It is almost sane, or sometimes you need to go there to address hardware issues or to get the utmost speed, but that's where you actually would not only wear a hard hat and pay attention, but where you would also nicely encapsulate that so that the users of your, let's say, semi-dangerous code are not being harmed, or at least you tell them to pay attention. And then there's the ill-advised and dangerous quadrant where you just don't want to go. The problem is C++ code might end up in all of these 4 quadrants or in all this area. And there are some questions I will try to answer where things actually are. So what can you do in user-defined class types? That's the power of C++. You don't have to pay for overhead. So if you define a class type, it can be as efficient as, let's say, int. But it can be more powerful than int, especially with respect to safety and sanity. So if you look at what typical class types do, a lot of these types can represent values. And that should be the dominant kind of types that you invent, should be value types. Because C++ is a value-based language, and if you're passing around values, nothing bad can happen. It's sane and safe. Because if I give you a £5 note, it's yours, and you can keep it. I just gave you chocolate. But passing around values, in contrast to a £5 note, actually if I pass you a £5 note, I still have it and you also have it. So it's not like chocolate or £5. Values in C++ you pass around, they get copied, and the receiver can do with the copy whatever it wants, and it will not harm the caller, for example. It will not harm another thread using the same value, because each one has its own value, which is good. No sharing, just value and computation. Returning values. With C++ 17, that even became more efficient because the compiler are enforced to do return value optimization from temporaries. There's another category not used that often, but also in the standard and popular. These are empty types. An empty type doesn't have member variables, or at least non-static member variables, and more or less it has one single value, so there's no comparison operators. Maybe. What are they used for? We will see in a moment. Like tags. Has anyone written an empty type? Okay, let's see if you have more examples in mind. And then there's the stuff where it gets more fickly and tricky and harder to do, is managing stuff. And that's also one of the big benefits of C++. What is the most important symbol character in C++ that you would use? Huh?
And curly brace.
Ending curly brace, closing curly brace. Thanks. So that's actually the powerful character in C++. The deterministic lifetime model of C++ makes the use of value types and everything just fine, and it allows us to create managing types that do sane things without leaking, without dangling, and so on. And then there's, a lot of people, last week I gave a talk where it said, okay, many people think C++ is a C plus object-oriented programming. And both of these things are actually the dark corners of C++. Don't go there if you can avoid it. There are some few situations where dynamic polymorphism is actually useful, but very often it's much overused because people either come from Java or just grasp OO, like myself 25, 30 years ago, no, almost 30 years ago. It was cool. Yeah, I now know virtual. Yeah, cool stuff. Don't. And I will tell you why later on. And there are some things that are not that easy to deal with that still require discipline. In C, almost every expression or statement requires high discipline. In C++, you can program at least sanely without having to figure out for each line if it has some bad effects. But there are some things, is what we nicknamed potentially dangling object types. So everything where you can have dangling stuff, where you refer to something and the object that refers to something else relies on the lifetime of that other object. Like, oh, it's something, if I don't get that feed, I'm dying. But I don't recognize that I'm dying when the other thing has died. So that's the thing. Dangling stuff is the only remaining dangerous part in modern C++, and there are means to actually avoid it, sidestep, or still use it in a sane manner. For example, usually what's safe and sane to do is passing a pointer or a reference as an argument to function call. If that function doesn't memorize the pointer or reference, it's very sane, because while the function is call works, the argument will still be available. It cannot go away unless you have multi-threading, but that's another story. Okay, Scott Myers taught us values. When in doubt, do as the ints do. The problem is the ints pretend to be value types, but they're not entirely safe. So think about an int, but not always. And I'll tell you why. So what are value types? The standard, or at least the Stepanov taught us regular types. And there's a concept of regular and semi-regular in C++20, but it has been around in the standard template libraries forever as a concept. And value types are typical regular types. They are default constructible. You can copy them from C++11 on. You can also move them. You can swap them, you can assign them, and you can compare them for equality. What is the important thing? To be regular, if I copy, and it's not the 5-pound note or the chocolate, if I copy an object, the copy and the original should be indistinguishable. If you copy and you can distinguish them, it's not a regular type, because some generic code might assume that if it copies something, it's identical to the original. The same is true for moving. The new moved to object has the same value as the previous moved from object, even if they are distinguishable after the move. The equality is, let's say, you can have equality without having the equality operator, because the objects would, or the value objects would behave the same, even if you cannot compare them. And in C++, before C++20, sometimes ordering is also required by regular. And in C++20, we will get spaceship operator. But I think we are not yet there to have understood it well enough to give good, safe, and sane guidelines for a lot of the C++20 new features that we are getting. So, value types just work. Use them. Don't care about performance. If you care about performance, use Godbolt, Compiler Explorer, to figure out if it really makes a difference. And the thing is, I thought it will make it simpler, but today I would say C++20 will make it differently. Maybe not simpler, because there are some subtleties with spaceship where even the standard people are fighting about. So I guess C++20 will be a very big thing. In Kona 2 months ago, we more or less made it feature complete. And that means I think it will be at least as big of a change as C++11, if not more. And it took us maybe, I would say, almost 10 years to get all the features of C++11 digested enough to fix them in 14 and 17, and also to give guidelines on how to use them better or more correctly, or what is the best way to employ them. Who has been to my lightning talk last night? So what did you learn? The rule of? The rule of Destemova. And that is something I came up with last year, more or less, or maybe 2 years ago, but I didn't come up with a name until last week. It's something that is from C++11, and there was a lot of discussion going on. It remembered me a little bit like the 1990s about OO design, if the square is a rectangle or a rectangle is a square. It's kind of things where it feels somehow it must be like that, but there are also opposing opinions on, oh, should be like that. So it should be rule of 3, so we make it rule of 5, but is that really the best way to spell it? And that's one of the things why I invented that. So if we look at our type categories and where we are going, there are things, value types and empty types just work. You cannot actually break your program by using value types and empty types if they are implemented correctly. There are other things like, if you look for, I have the pointer so it goes for the video as well. If you look for OO polymorphic types, you might want to use them, but you have to use your judgment to actually use them. And there are things like plain pointers that are just don't do that. Dangerous. If the plain pointer is actually owning memory, no, don't go there. We have unique pointer. The core guidelines had that in that thing like an owner marker for pointer types. Don't. If you write owner, make it a unique pointer immediately. You touch that code anyway. And there are other weird combinations, and I've seen people use that, sometimes without knowing, sometimes with good intentions, but not knowing the mechanics of the language and what happens underneath, and don't go there. The question is, where are int, double, and bool? And please, I think there's one guy here who will actually tell you a lot of things about, or know a lot of things because of the C++ quiz, where you do things like that. But where are int, double, and bool here? Guess, which quadrant? Are they here? Check, good. Really? Who thinks there are sane but dangerous? Ill-advised and safe?
Yeah, I guess you're right.
Or ill-advised and dangerous? Let's see. Example. Are the primitive language types sane and safe? Safety. Int, char, bool seem to be their regular value types. Looks okay, copying, equality is given. But they also have a lot of interesting operators. And this test, what's the answer? It will fail because it's either yes or no, but what is the answer? That's a pub quiz, not pub quiz, a C++ quiz question. What's the result? And why is it running? I could show it in the IDE, but let's hover. What type is I?
Int.
As a constant, or int const. Throt is a bool. What is the value of throt? Huh? Well, 41 is not divisible by 3, so it's somehow 1 or 2, but because it's a bool, it's true. Now we have true bit AND with 42. Is that true or false? Come on, where are the electrical engineers? Huh? Are you sure? What is this operator doing? Bitwise AND. What is the value of true if you convert it back to an integer? You should know. Say it again. You get integral promotion. This is an int, this is a bool. A bool will happily convert to an int. True being the value 1. So you have 1 bit AND 42, which is even. So the answer should be no. I'm not even sure I even stole something like that from your quiz thing. So we have this simple thing bool, but it very happily works comes from an integer, but just throwing away everything or making true everything that's not 0, regardless which number. So it's treated as a number and more or less truncated. And then it happily converts back to be an int, but actually just using 1 for true and 0 for false, and happily take part in integral things. And very often this has not been meant to be used with a bit AND. So using bool with a bit operation is usually flagged by static analysis tools. Do you really think you do what you're doing? But sometimes people actually do it deliberately to avoid to have all the operands actually evaluated, which you would not be able to get with the logical AND. So, bool, is it sane and safe to use? The safety critical people very often think about, oh, does the code do what the programmer thinks it does? And just by seeing code like that, it might not be doing what the programmer thinks it does. And you have a hard time figuring it out, and better write test cases if you're in doubt to actually see that things are bad. Other example. Double. We have a vector of double. C++17, class template argument deduction, the vector of double. And then we have a set of double. And we insert every potential division of these numbers into the set. How big is the set? The test case fails just for that. So it's not the all combinations minus the one that would give 1. Why?
It's a set, so something two of the things are the same value.
That's a good trick, yes. But why? So the set might end up unique value, so it's not a multi-set. So if you have the same value combination, it will not show up twice. That's why I have these, okay, I subtract all the, if x and y is the same value from the vector, all will result in 1, so I add 1. But there, what's the problem here in that code?
You would have all the numbers.
I have not a number because I divide. First, I have infinity because I divide by 0. But the very first combination is I divide 0 by 0. And now we have to look at Anders, who will know the standard, what the standard says about that. Huh?
I don't know much about close.
Well, dividing by 0, even for floating point values, is undefined behavior unless your double type is actually conforming to the floating point standard the C++ standard refers to. And there's a check in numeric limits to see if dividing by 0 is allowed. And dividing by 0 will give you, let's say 1 divided by 0 will give you infinity. But dividing 0 by 0 will give you not a number. It's almost like in JavaScript. Not a number. But what is the property of not a number? Who knows? You should know.
The higher bit is...
Say it again?
Higher bit is set to 1.
Not a number is not comparable with another double by operator less than or standard less, which is used by set. So it's neither less than the next one that gets into the set, nor the next number that should go in the set is less than not a number. What does that mean? They are considered equivalent. So once you have not a number in your set, all other values are considered equivalent, so already in the set, which breaks up. So the set will actually have one element in there if dividing by 0 actually is defined on your compiler, and it will end up with one element, not a number. Yes?
Why do you consider that to be a problem with double rather than a problem with set?
Because first, dividing by 0 can happen with double, and I happily divided by 0 since ever, because I thought, okay, I will get infinity and not a number, but it's not guaranteed by the C++ standard, unless you query for that. And the problem with, it's a problem with double, because the double doesn't actually fulfill the concept of what the set template argument is asked for, because it requires a total order on the elements, and with the not a number thing, doubles are not totally ordered, unless you use a special ordering function, but that's not the default for a set of double. So the question was, why it's a problem with set, with double and not with set? The problem is you combining these two is a problem, because one problem is with double, dividing by 0 is not always guaranteed by the standard. And the second problem is doubles don't sort properly enough to be used in a set. Bad things, even with the built-in types that seem to be sane and safe, so they're not that sane. What did I want to say here? Oh, there's a nice bug, yes. Who sees the bug? That's a classic. First thing, the bug is don't use counting for loops. Use range algorithms.
Is this loop infinite? I mean, E is unsigned.
So there's one candidate saying the loop is infinite. Why?
The out of E would be unsigned and never reach.
So we have an unsigned, the type of v.size minus 1, because v.size is an unsigned type. Subtracting 1, it remains an unsigned type because of the integral promotion rules. So I will have an unsigned type size t. And an unsigned type can never be greater, is always greater equal to 0. It cannot be negative. So we have a loop with a true loop condition, which is endless. And what will the compiler do with an endless loop? It'll consider it undefined behavior and maybe optimize it away, if you're lucky. So there are people who say, okay, the return type of size is wrong. I think they are wrong. It's just a problem that the built-in types don't work properly enough.
Size could be 0 as well.
I didn't get that?
No, size could be 0.
Then you have E minus.
But it's an endless loop regardless. If size is 0, I will be very big. But it's true anyway, so there's nothing to do about that. It's just wrong. So what are some of the problems? One thing is integral promotion. I maybe know a handful of people who can cite the integral promotion rules and actually know what they're supposed to be doing. Many people think they know and they're slightly off. And the problem is if you mix signed and unsigned types, it always gets hairy. And the bad thing is signed integer overflow is undefined behavior, which is there for historical reasons. And the problem is we can't get to the carry bit. Who's not knowing what the carry bit is? Okay, don't care. And the other thing is there are automatic implicit numeric conversions, and that's where the C++ types more or less breaks down. We freely convert between integers, floating point, and bools, and sometimes even pointers and bools. And if you have complicated mixtures or don't care, sometimes you get warnings, so you want to get rid of warnings, and sometimes it just doesn't make sense. And we have these special values of floating point numbers because they are not real numbers, but something that is close enough and not a number. Except for the JavaScript programs, it gets very often forgotten to care about it. And the problem is, it might never happen, but sometime you might call either a computation function that gives you not a number, or you divide 0 by 0, which is also not a number. Primitive types, even in the standard library, you find very interesting code pieces. So the return type of standard distance is the difference type, or a putative T. It's a signed type. It's put into an unsigned type variable. And just to make this thing not warn, because if you compare signed and unsigned integers, most compilers give you a warning because of this overflow that's possible to happen and being undefined behavior. So, okay, we want to avoid this warning, and we know first is always before last, so the distance is always 0 or positive, so we can safely store it in an unsigned type to actually get rid of that. But if you look at the further uses of n, they're actually used in places where it actually has to be a difference type. So one can argue, why didn't they cast this expression to a distance type and then use the default return type of std distance? I'm not exactly sure, but if you know that's from std vector somewhere in the lib standard C++. So if you have to use cast or cast expressions in your code, that's very often showing you a design failure. Be aware of that. And the built-in times are guilty of the free automatic conversion that give you bad things. So my guideline that I like to teach in the future is actually whenever you're using a primitive type, provide a strong type wrapper around these primitive types. Because when you have a function that uses several parameters of the same type, it's very easy to flip them around and call it wrongly. And the primitive types have several of these problems. Very often you have functions taking 2 ints, but which is which? And there are people coming up, oh, I need named arguments for C++. Wrong, you need the right type abstraction for your arguments. So if you look at int, double, and unsigned, they all require high discipline that we might not have. So the better thing is to apply the whole value pattern, and even string is some kind of primitive, but at least it just works and doesn't give you that much chance for undefined behavior. So the example I had, I have check counters, 2 different counters. One should be 0, one should be 1. How do I know which is which? Okay, if I look at the specification, I see check counters. One has the wait counter and the other one is a notify counter. And it's for test code, testing student code in multi-threaded environment that they do the right thing. And if I just use a type alias, I might even clarify it's a wait counter and a notify counter, but type aliases like type defs are not strong. You still can mix up these things without the compiler telling you anything about it. So what we need is something like a strong alias to get around that. And this, why do we need that? I just met a person last night who was at the Europlop conference 1996, and he told me it changed his career or his life or whatever. And even earlier, what Cunningham, the inventor of the WikiWeb, by the way, if you don't know, he published at the Plop conference a year or 2 before the checks pattern language, and it's about checking arguments. And it says, okay, if you use a domain model where you parameterize stuff there, methods or functions, very often you use fundamental units of computation, ints, numbers, string. The problem is they are not really giving you an abstraction. And in C, you don't have the ability to do your own abstraction. In C++, we can do that. We can define our own types that are as strong as the built-in types. So the primitive types can represent almost anything. Like in Fortran, everything is a number, and you can do a lot of that with that. But it means nothing in isolation. So what does 42 mean? There are several positions to what 42 means. It's just a number. So what you would do is actually you model the arguments as types. And we use value types for that because we pass by value. We provide the functionality that these domain modeled arguments and attributes actually have by function and operators. We provide checks that only valid values actually make it into these types with constructors, or even output are presented as output accordingly. So it's not only 42, but 42 miles to run for the marathon, or 42 kilometers to run for a marathon. And no implicit conversions. That's a key thing. You don't want to have the 42 kilometers to mean 42 miles or 42 chocolates. And that's a key thing. And that's why all the built-in types are not that well. And in C++, in contrast to most other object-oriented languages, you can do this without any overhead, which is great. Whenever you have a function taking multiple arguments of the same type, it will be called wrongly. I stay with that. So with our wait and notify, we can mix that, and I guess you get what I want to. So the simplest actually thing that you can do, the minimal thing that you can do to protect your counter is wrapping it in a struct. And that's all you need to do to get towards sanity. You can still access the count and so on. You might actually even provide overloaded operator for the exact set of operations that you want. For a counter that only increments, that's sufficient. And the thing is, now, with 2 distinct types, wait and notify, you can no longer call the check counters wrongly. Because the first one must be of type wait, the second one must be of type notify, and they're distinct types. Then you come up, oh, I don't want to repeat myself. I do more about that. So what the problem then you get is, oh, you have a base class where you pull up all the features. The problem is C++ happily converts to public bases, and you lose all the benefits that you intended to get. If you then use the base class, for example, here, in that assertion, it will be called operator equal, and it will happily convert a weight with the base class and notify B bad. The other thing that can happen is, whenever some crazy person who shouldn't do it puts some of the subclasses on the heap and use the base class pointer to delete it, because it's not having a virtual destructor in the base class, you will have undefined behavior if you delete it through a base class pointer, which is also bad. So what you can do is actually you can use a mixin class and use the curiously recurring template parameter pattern where you pass your own type as the type into the mixin class, and the mixin class will actually implement all the counting stuff. So you have distinct counter, wait, and notify. They still inherit, so the delete via the base pointer is still there, but you can do something about that. But there's actually no need to allocate that on the heap yourself if you really need to. The problem, so now our example from before, comparing notify and the wait counter does no longer compile because they are distinct types and no longer related. Now, if I write these wrapper classes and my whole value types, or in general value types, should a value type be default constructible? And we apply the rule of zero. Either we have a default constructor, a default constructor, which should be the sane thing to do, or we don't have a default constructor, but we don't have any constructor, then it's the default constructor is there and will do value initialization. One rule is whenever the operation have a natural neutral value in the type domain, like integers, if you take addition, 0 is the same default value because that's the unit value of addition. It will not change the value when you add it to something. The neutral value depends. For example, 0 is a bad thing for multiplication. And there's a question, sorry, I can't see the audience very well.
But now we have to test, write, and maintain that wrapper. Is it worth it?
Say it again?
Now we have to test this, now we have to maintain this, now we have to make sure that this is also fine.
That the is the inheriting wrapper or the base class? Both of them. For the base class, I'm working on it to have a safe and sane set of base classes to mix in operators and everything. But that's you will see at C++ now in a couple of weeks. It's not done yet. But wrapping this helps a lot, especially if you have multiple cases where you actually have distinct things like Marslander crashes would not have happened if you have even these simple wrappers around that. So it really, if you talk about safety critical code, you better not want to mix up units and stuff that you're using. So wrapping really helps. And even, I believe it was Björn Fahler last year showed about this strong typing library and kind of, you have a message processing where you just mix up sender and receiver who are already distinct types but just addresses without having a distinct type for sender and receiver. And those are bugs that are very hard to find. And that's also something you not want to do. So there's no free lunch, but the wrapping actually, it might give you slightly more source code, but it will give you, let's say, more maintainable source code because the signatures actually spell out what they're doing with these arguments. Now let's get back to the default construction. If you have a natural neutral value, yes. If the initialization requires you to maybe have a two-step initialization. You might want to have one, but I'm not sure if that's a good idea. Better provide a factory or in-place lambda for initialization. If there's no natural default value, like you're representing playing cards, what is the default? Is it an ace? Is it a 2? Is it a king? There's no natural default value, so then don't do a default, provide a default constructor. And there are also things that should enforce reasonable initialization, like a cryptographic key. You don't want your code to have a default constructed key that is 0, or not even random. Don't do that. Don't have a default constructor. So the regular concept doesn't always apply for all kind of value types. Well, now, even if you do units, beware of what the mathematicians call affine spaces, where you have stit chrono is a thing where you have absolute values, time points, and relative values, duration. And if you subtract one absolute from the other absolute, you get the difference between them, which is the duration. If you add a duration to a time point, you get a new time point. But adding 2 time points just doesn't make sense. Adding durations makes sense. It's just a longer duration or a shorter one if one is negative. It's the difference between position and direction in a 2D or 3D space. For example, a lot of games use a 3D vec, which is more or less 3 values, and it can be used to present a position, but also a displacement. And if it's the same type, you can mix them up and maybe add 2 positions, which doesn't make sense. That's also something to watch out if you define your own unit types. And I've seen units library that just forget about that, because they tend to have the same dimension and aren't the same thing. So in our example from the standard library, we had the size type, which is actually distance is a relative type. The comparison of capacity and size, which are both absolutes, will give you a relative type. And the result of that subtraction should be a difference type, like the distance. Actually, what this does is computing the distance between size and capacity, if you would think about it. So this type is wrong. The result of this operation is wrong, and that makes all that code so clutchy by casting the n. Do it better. You can do better. So what you can do to save you implementing all the overloads is actually mix them in. And I'm working on a small framework to having strong types without too much overhead, where you mix in operators and get what you want. And actually, by empty base class optimization, these things stay as big as the type that you actually wrap. And there are others who work on these strong wrappers, and I hope I will get it right. And I forgot about something that I was pointed out this week by Loic Joly. You still have to care about not being able to delete them via the base class pointer. And in C++ 17, the new thing is a lot of things remain aggregates, which is good because aggregates are very cheap for the compiler and usually cheaper than a structure with the constructor and so on. And there are some more optimizations that can happen when it's an aggregate. That's why I'm trying to get that feature done with still saying an aggregate. It's not really encapsulation, but it's distinct types that helps you. Empty classes. Yeah, still good. What is an empty class? Are they useful? There are songs that say you don't get something for nothing. There's talk by Kevlin Henney, there is something for nothing. And in C++, you get, with empty classes, you get something for nothing. And they're completely safe and sane because if there's no data, nothing can go wrong. And by default, they copy nicely and just work. and they might actually be able to be useful, like CRTP mixing classes with adding friend operations that are hidden friends and two existing classes to provide them with additional operations. One other use is tag types. So you have a type that is used as a function parameter type to distinguish an overload from other overloads. For example, in the class optional, we have a special argument type called inplaceT, and there's a value for it in the standard as well. So if you have an optional of string, you can use this in-place constructor to construct the string that resides within the optional without having to move or copy the string into the optional and saying, okay, this string in the optional has 3 times the letter A, because these arguments are passed to the string constructor directly. And you need to have that special version to actually distinguish what you pass in for the constructor to get that optional. One might wiggle around by having a special factory for these optionals, but with using this constructor, we can actually make sure it's using that in place, constructing the thing in place without additional move or copy operations. In the standard library, there are algorithms that use the iterator tags to distinguish different implementations for different strength of the iterators. For example, there are algorithms that can be implemented faster by using random access iterators, but they still work with bidirectional iterators, and that's how the mechanics work. You have the algorithm call interface with the iterators, and then your dispatch is using iterator traits, iterator category, and you actually construct an object of that type, which is empty, and then the corresponding overload is actually chosen when you call that algorithm. We also have a type that's special. It's nullputter T that has one distinct value, nullputter, but at least it converts to other pointers to be, or is comparable to other pointers, so that's slightly different from a plain, pure tag type. We have a whole bunch of means to actually do compile time computation with empty types, where we, for example, represent values as types. There's integral constant, the true type, false type. Even for rational numbers, we have split ratio for representing the millis and megas in chrono. We have integer sequences with more or less a sequence of integers representing a type. And what is that used for? For substitution failure is not an error mechanics. To select template specializations, to select overloads. It's for ratio and other dimensions maybe in the future. For tuple element access, we use integer sequence to implement that and other things. Anybody using these traits in a daily basis? Okay. Anything I forgot where it's useful for?
Pub quizzes.
Say again?
Pub quizzes.
Oh, for pub quizzes. Okay, yeah. So we can do a lot of things actually at compile time, even though this code piece actually does it at runtime. So we can see if something is an integer and run away from it, or even if it's other things. For example, you can use it. Okay, I have one example I have in my class is implementing a sack, which is the German word for a bag. So you just can put things in and you get things out at random, but you don't want to put pointers in there. So we have a static assert that checks if it's a pointer, if it's not a pointer but an object type, so we can actually put stuff in the sack. We have also a version where we actually use a template specialization to avoid getting pointers into a sack. What else can we do? Yeah, we can do actually using the traits for computing new types from existing types, more or less everything that you would do on the language level by adding pointer and reference and everything. You can also do at compile time by taking an existing type and wrapping or unwrapping things like that. So to wrap, you can add const or add value reference, or you can actually remove all extents, remove const volatile, and check if it's the same type, and even decay would actually decay the same as you would pass that type as a function argument. Now, how does empty base optimization actually work? If you look at an empty struct, it still has a size of that is not 0. Why is that so? The thing is, each distinct object in C++ by definition must have a unique address if you take it, or are able to take it. So therefore, you cannot have, if you have a vector of empty objects, they cannot be at the same place because they must have distinct address. So for the memory, it must be at least size 1. But if you wrap a simple type, the size of that wrapper is exactly the size of an integer. There's no additional overhead. And if you combine such a type that has something in there, and then do something like a private inheritance from an empty, because empty might have actually friend functions that you want to get to, then the size of the combined type, empty itself doesn't take any space, so the size of the combined type is the size of plain. That's how you can check for the empty base class optimization. It won't work if you only have one base class, but it works if you have multiple base classes and the first one is not empty. You will get actually no additional space for empty base classes. In C++20, that's even possible for empty member variables. So if your class is not empty, you can add member variables of empty type to access their functionality that's hidden there by using the noUniqueAddress attribute. But that's future. When doesn't it work? There are a few reasons because of that rule of, every object must have a distinct address. If you combine an empty base class with a class that has an empty member and they would lie on the same starting address, you wouldn't get empty base class optimization. So for example, I inherit from empty and I put it as a first member variable that would happen to be on the same address, so that the compiler cannot put the base class object and the E on the same address. So it actually needs, with padding, so the size of my attempt of an empty base class optimization is actually 2 times the size of an int because of the padding that usually happens between the empty base class object and the object E and the alignment of the integer. And if we go further, what I wanted to say with that example. I think that's, I have the empty base, I have the empty base class and now I have an object of this type EBO. EBO is aligned already at least to an integer because it's the size of 2 integers, and we have another integer and we have the empty base, and somehow that must go together, so we have unique addresses, and that ends up, due to padding, to being 4 times the size of an integer. So if you want to have empty base optimizations, you must have one object that is not empty, and then you can inherit from all these empty objects, and then things work out fine. And I don't want to go into, this is my attempts to have these mix-in things with the empty base classes, but that code, as shown on the slide, is not safe yet because of the deletion problem with the base class pointer that I didn't think about because I was never intending to put things like that on the heap, but users might do. Therefore, it's not released yet. But there will be my attempt to get it done. And if it's broken, tell me after C++ now, or I will learn there. Other things for empty base class optimization. 2 years ago, I had a lightning talk about how to manage C pointers with a unique pointer without additional overhead. The classical example was actually to use a unique pointer with using decal type, the free pointer, and then passing the free pointer to the unique pointer constructor. The problem is then that you get a unique pointer that is twice the size of the plain unique pointer. And the trick is to actually have a deleter object with an overloaded call operator for deleting with free, and that deleter object is passed as a template argument to the unique pointer. And then the template argument will actually be able to, the unique pointer implementation, we use empty base class optimization to get rid of the additional object by inheriting from these free deleter, and will allow you so that there's no overhead in size from a plain pointer. So that also shows you unique pointer allows you, is a perfect replacement for plain pointers. We just cannot forget to get to free or delete the pointers. So there's no excuse for not using unique pointer. There's one thing I do with my students which is also somehow requires discipline. So it's kind of a hard hat thing, but it's not completely insane. Sometimes you want to have adapters for existing class types. And if you only exclusively use the adapted type, you're fine because nothing bad happened, unless you do these delete via base pointer, which you don't. So for example, we have an exercise, make a set that has the index operator so you can iterate with your bad loops over that, and that allows you to adapt standard set, and inheriting constructors actually allow us to have these to have the same constructors as set, and then provide, because we have public inheritance, we get all the member functions of set, and we have additional ones, index operator and add, and front and back, and be able to treat the set as a sequence range as well as we would use with vector, for example. Again, hard hat area, not always a good idea. Now let's get to the gallows. There was a talk last year by Jonathan Müller on I just wanted to point to something, which was a lot of fun. I'm not sure he was perfectly right in my sense of what is right, but it was still a very inspiring and good talk. And 2 months ago in Kona, we had the meeting of the programming vulnerabilities group with respect to C++, in combination with the undefined behavior study group of C++ committee, and we came up with something that we nicknamed potentially dangling object types, or potentially dangling types. Describe objects that depend on the lifetime of other referred objects. If a referred object's lifetime ends before the referring object, one risks undefined behavior. So it's even possible in C++ to create a dangling object while you construct it. So you more or less create an object that is on the gallows while the trapdoor is already open when it comes into existence. So be careful. That's where you have to actually be careful. And you can make it more sane. For example, if you have a managing type that manages stuff, you might need a pointing type. Sometimes it's nullable. You have to check that you don't dereference a nullable pointer, because otherwise your program explodes. Polymorphic types. For good use, you need to use references to them, to the objects, to get the dynamic polymorphism. That means you need to use pointing types somewhere. And if they can be dangling, then bad things happen. So what you can do is don't use plain pointing types, use smart pointers that manage the memory, which gives you at least the lifetime guarantee that you wouldn't have a dangling pointer. A unique pointer cannot dangle. Good. It can be null, so you have to check that, but it cannot dangle by definition. And if you pass these pointing types, the potentially dangling types, only down the call chain and not spawn a thread from them, then you're safe. Because the mechanics of C++ guarantee, at least until 17, that whenever you pass something to a function, the argument will stay around until the function returns. So you can actually take it. And even if you pass it down by const reference, on the call side, it will live as long as the function you call exists, or is active. So, but it's not the only pointers that are these potentially dangling types. We can define our own class types that refer to other objects. And this means we have to argue that the lifetime of a referred object doesn't extend the lifetime of referring objects, of the potentially dangling object. So the problem is very often, like pointers, these types are regular, so you intend to copy them around, but the copy also transfers the burden of taking care of the lifetime. And sometimes they are regular, you can copy them around, but they are not value types because they don't exist out of time of space. They depend on something else. And if that something else is dead, you just open the trapdoor on the gallows. It can be invalid. And categories, it's iterators. And the bad thing is about iterators, you get them back from functions. And if these functions don't come as member functions of the object that is alive, it's very easy to get a dangling iterator back. We have pointers. Iterators come in a special kind. You can have past the end iterator. They are valid, but you cannot dereference them. And we have iterators that we might keep around while the container changes, and then the iterator gets invalidated. And the rules of iterator invalidation can be very tricky because they are different between the different categories of containers. So whenever you push back something on a vector, all iterators of that vector are no longer valid. They might point to memory that's no longer in the vector. When you insert into a map, previous map iterators remain valid, which is a strange thing. And getting that right, especially if, I don't need that set here, I just use vector, it's faster, and sort it from time to time. And maybe someone else assumed it was a set, this data structure, and bad things happen. So never store iterators too long. And there's a new category, string view, introduced in 17. Who's using string view? Who has been hurt by a dangling string view? One? Who has been hurt by a dangling string view? Okay. Some. The others don't have recognized yet. Another thing very often forgotten is reference wrapper. It can be used to actually implement something where you don't want to use a pointer because it cannot be null, but you want to have assignability, so you make your member variable instead of a reference wrapper that can be reassigned and copied easily. Again, this is internally implemented as a pointer, and because it's a reference, the dangling danger is there. I think I said almost all of that already. Again, iterators refer to other objects in containers. We have these non-dereferenceable iterator values. And even though some libraries try hard, invalid iterators are usually not detectable. Reference wrapper, if we look closely, we see it's implemented as a pointer. And again, I said it has some automatic conversion to a reference, so it can be used like the reference almost always. It also has interesting thing like an overloaded call operator, which makes it useful from the point where it came from. But it doesn't overload everything. The good thing is it cannot be null. You have a hard time creating a reference wrapper that is null. In my book, the best thing is not having to use plain pointers. The C++ core guidelines tell you, okay, if you see a plain pointer, it means it's a pointer to a single object. The problem is, with migrating code base from the pre-C++ core guidelines to post-C++ core guidelines, you might not know if a pointer, when you see it in the code base, actually means is a single object or it's just an old plain pointer that you have to deal with. So there are proposed wrappers. One was called observer pointer. It's a little bit more elaborated than what the alias there says, which says, okay, this is a single object pointer that borrows the object and doesn't own the pointee. It's in library fundamentals TS, but it's not in the standard of C++20 because people couldn't agree on what it actually means, or is it really useful. The core guideline author said, no, it's not useful. We have that concept as a single pointer. Anthony Williams implemented in his library a free version that's called object pointer that will automatically convert from a unique pointer and a shared pointer. I had some discussion yesterday with him, and I might actually derive from that and improve its implementation by, for example, getting rid of its specialization or its implementation of standard swap, of its swap operation. The only good pointer to use, I can say, if you need heap allocation, use make unique and unique pointer. From all the shared pointers we have so far, that's the most useful one. And don't use delete, free, new, or malloc in your code. Who confesses, I still have delete in my code base? Okay, about maybe 25%. Get rid of that. Use unique pointer, full stop. There's no excuse not to use unique pointer today. There was in 11 because we didn't have make unique, it got forgotten, but no longer. Shared pointers are a strange beast. I recommend you look at a talk by Nico Yosutis telling you what bad things can happen if you use shared pointer too freely. If you really want to share objects everywhere, make sure that they just live and don't rely on the reference counting. So one recommendation is if you have a large set of objects that you want to share across stuff, put unique pointers in a vector and maintain the sharing via reference wrappers or object pointer, and just make sure that the vector with the unique pointer outlives all the usages, which might be a better means to get there instead of shared pointer with its huge reference counting overhead. Views, string view or span, which we'll get in 20, are also reference types for contiguous memory, but nevertheless, they rely on the existence of the object they're referring to, and they can dangle. We also will have not only the single dimensional span, but maybe in the future also array views with multiple dimensions, and that's, I'm not sure if we get it. Michael, do you remember if you have the view class in 20 or not? The proposal has been around for some time, and some forth and back design going on. I'm not sure it was voted into 20. Okay, but span will be, yeah.
All of the views will be the ranges.
Say it again?
All of the ranges views will be there.
The ranges views also are potentially dangling. So string view is special because it's so convenient to get rid of char pointer arguments. It has a better performance than passing by string const reference. It is safer than char const star because it comes with the length. But if you have existing APIs that use character pointers and string references, it's very hard to retrofit them with string view. Either you have additional overloads or you lack template argument deduction. And I tried for the standard and failed horribly. So be careful if you retrofit string view to existing interfaces. If you just have char const star overloads, then just change that to string view and you're better off. But you have to change the implementation of your function as well. What you never should do, returning a string view, because that's a case where you can easily, immediately dangle. So never trust a string view that you get from a function back. It's like never trust a character pointer you get back from somewhere. Even in C, it was very good practice to use throughdup to always get your own copy of your string that you got back. Pointers don't. The thing is, all pointing types live in the dangerous half of my 4 quadrants, and they require programmer discipline. In C, everything requires programmer discipline. In C++, only these require programmer discipline and the types inherited from C. The bad thing is a lot of code just compiles. It even works most of the time, or just seems to work. And it's easy to break code by changing the container. So do not rely on the iterator staying valid if a container can change. And there are ideas for static analysis. Herb presented them last year. I have a student who tried to implement part of that, but I'm not exactly sure how far it is. I just got the report yesterday, so I haven't read it yet. So I'm not sure how far he got. So that's where you have to put on your hard hat and your protective gear and be high disciplined to care about it. That's is something I don't want to show. So again, temporaries are dangerous because they can dangle. I want to say something about managing and pointing. So we said always down the call chain. Managing types come in 2 flavors. One is RAII, non-copyable, non-movable, and the other one is unique. You make it move only. And there's a third combination of, okay, a managing type that is also a value type, which requires expert level skills like std_vector. Who has implemented std_vector? Marshall is not here today. Oh, there's one. It requires high discipline and high skill, and it's to do it correctly. So how do you figure out if something is a managing type? Whenever it has a user-provided destructor, then it is a managing type. Typically, such a managing implemented destructor that's not defaulted or empty does something. So the level 0 is used for scope-based resource management, like LockGuard. You apply the rule of Destemova. So you delete the move assignment operator to get rid of all copying and move operation. Watch my lightning talk last night. So if it doesn't move, it's also not copyable automatically. And you can still return it from a factory if you really need a factory for some special setting things up, because of the return value optimization guaranteed by 17. The level 1 is a slightly more elaborate thing where you say, okay, I want a unique representation wrapper for a resource. The canonical example is standard unique pointer, who does a little bit more. I tried to provide a unique resource type for generic resource management for C++20 and failed, but it will come into the standard library fundamentals technical specification version 3, and I'm still trying to have compilers understand my implementation well enough so it's portable across compilers, which is not yet. But the requirement you shouldn't forget about, if you want to make your managing type correct, you have to rely on to detecting the moved from state so your destructor doesn't delete it twice. For pointers, it's trivial, we have null pointer. But for other types, it's not that trivial. For example, if you want a manager for, let's say, file handles, 0 on POSIX is a valid file handle. So you cannot just use 0 and, oh, if it's 0, I do nothing. You might invent another extra value to make sure that you don't call close on a file handle that's valid. Or or not calling close on a valid file handle because you think it's already moved from. If you have 0 and 1 complexity, the complexity n is much bigger, at least 10 times, for implementing stuff like standard vector, especially if you do it generically, where you have to employ things like a placement new, maybe even launder. Don't go there. Leave it to the experts. And I'm running out of time. I will not show you the further examples. So if you want to have a look at the unique resource, it's on my GitHub, and you can find it, and please help with the implementation across compilers. I'm still suffering from being too bad in Visual Studio to get rid of the compile errors in the current Visual Studio release. Dynamic polymorphism. Sean Parent, inheritance is the base class of evil. Don't. Now, remember, this is Howard Hinnan's big table on what you get when you define something. If you define a destructor, you still get copyability, fortunately not movability. When you define a copy constructor, you still get the automated copy assignment, and so on. The red parts are really dangerous. The problem is, if you want to have virtual, you have to declare a virtual destructor in the base class. Now, I came up with, okay, if you want to do that, you actually want to be here where you have a defined destructor and no copying or move operation, and you get there by defining the move assignment and define it as deleted. That will get you don't get a move constructor, you don't get a copy and assignment and copy constructor. And that's the same thing to do for classes that have a virtual destructor, because if you inherit and you would make it copyable, you would get object slicing, which you don't want to get. And that's what I called the rule of Desdemova. So it's not Desdemona, but Desdemova. If you have a destructor defined, delete the move assignment, and then everything is fine. This is the same thing to do. It's the least amount of code to write. There are people who say, oh, I do the rule of 5. Don't. The rule of 5 is expert only and should only be employed if you have reasonable bodies for your copy and move operations. It's for things like std vector. For simple RAI types and for OO base classes, apply the rule of Desdemova. What do? We apply the rule of Destemova. Remember that. Take that home. Dear video audience, take that home. Rule of Destemova. OO design. Just one example of very good OO design. A person can be a student or a professor. Is that a good OO design? Would you put that in a database like that? Who's done that? I'm guilty. Don't. We have to have pass by reference. We have instances, and we apply the rule of Destemova. So whenever you think, oh, I need to write virtual, if I would be responsible, you would have to sign a 20-page form in triplicate, hand-filled 3 times, non-copied, non-carbon paper in between, before you apply virtual. Stay away from virtual. There are a few cases where you have runtime behavior, and there's another talk about how to employ a standard variant instead. But if you have a fixed set of subclasses, that might be just sufficient. And again, just an example piece of code. This is a drawable and composite pattern applied. And there we also have the rule of Destemova, which gives us, we have to have a virtual destructor in our base class, but we get rid of all the copy and move operations and just circumvent slicing. And I don't want to explain all the things that come with it. We can even put it with reference wrappers into the vector without having pointers, so it's possible. But that's something for you to take home and look at it, because we're running out of time. There's one thing where you might want to employ virtual, but that's not tightly capsulated. It's type erasure, where you can actually get value objects in a generic sense. Standard function is something like that. Standard any is something like that. And Sean Parent gave a talk last year at CPPCon where you can actually do a lot of type erasure to get rid of all of inheritance on the user side by wrapping it into a type erasure class. And the concept is that you have something where you have an abstraction that is encapsulated, and whenever something gets put into a widget, you have a model class that is templatized by the thing that you put there and store it inside. So that's an implementation that I made based on Sean Parent's ideas, and the time is running out, so it takes about 45 minutes to explain all of them, and I just wanted to flip through so you can have the slide and the code showing that. That summarizes what I would like to show you. Okay, we have the concept of aggregates, where you have no constructors. Everything is defaulted and it just works. That's the simplest wrappers you can do. You can have additional operators by mix-ins. Just have to take care that you don't delete via the base class pointer. We have simple value classes where you might have some constructor. You might resurrect the default constructor if you consider it's defaulted. And then we have the manager types where you have a simple managing class, RAI class. We have a destructor that is implemented. And you apply the rule of Destemova to get rid of all these unwanted copy and move operations. You have the unique managers, where you have the implemented destructor, but this one needs to take care about the moved from state to not destruct the moved from object. And you have to implement move assignment and move construction and be clear what the moved from state actually means. And then we have the managers that also can be value classes, so you can copy them like standard vector, which means expert level implementation of all the rule of 5. If you have OO base classes, again, we have to have a virtual destructor, which we better only have equals default. Never mix too many things together. If you have an OO base abstraction, your virtual destructor should be defaulted, and then apply the rule of Destemova to get rid of the potential slicing that you might get. And then there's the last thing that's also a very expert level thing. Even if you follow Sean Parent's advice, you might have a constructor And you have all these expert level implementation doing the type erasure that you can get, where you have OO plus value semantics, and there should be another row, but I haven't been to the talk yet and I haven't seen it about how to apply variant for getting these runtime variation. That's the whole map, and we are running out. What are the takeaways? Learn to appreciate the C++ type system. Every cast is an indication to think and refactor. Model with value types almost always. It's a little like almost always auto. But be aware of if you do model value types, about the affine space between relative and absolute dimensions. Read primitives using whole value, read it up, 25 years ago almost. Be aware of the required expertise and discipline for manager types and creating OO hierarchies. Remember the rule of Destimova. Be disciplined about pointing types. Run away from types with weird special member function combinations, even if they are defaulted. Don't go there. It's like trying to cut your toenails with a chainsaw. And usually they're just wrong. And sorry for that. Ah, come on. That's when you have too many clicks for the slides. Questions? We're into break. I can't do that. Final questions. I have a question of you. Who is using unique pointer tomorrow? Yeah. Who's still having chocolate? You can grab the chocolate on the seats next to you. Any more questions? Then go home. Remember the rule of Destimova.